Okay, let's begin our next unit, which is polynomial functions. And the first part of polynomial functions, we are going to look at simply identifying what a polynomial function is. So we're going to look at all the different ways we can do that. So our learning goals for this lesson is to differentiate between functions and relations, okay, which we have already reviewed, recognize polynomial functions, and recognizing them from their graphs, from their tables, and also from their equations, okay? That's important. And stating domain and range for a given graph. In terms of some background knowledge, in terms of what polynomials are used for, just some of the examples. They are used all over around us in our real world. And just some of the examples is in physics, for example, in economics, meteorology, roller coaster designs, bridge designs. They are used all around us, and we probably don't even realize it and know it. But it really is an important part of our world. And so we're going to look at understanding polynomial functions a little better. We already should have a pretty good grasp on linear polynomial functions and quadratics. So we're really going to kind of refresh our memory with that and then add to it cubic and quartic functions and even beyond that as well. Okay, so let's get into our lesson of identifying polynomial functions. And before we do that, we really should look at defining what a polynomial function is. Okay, so there's several points I want to make here on how to identify or define a polynomial function. So the first thing being that it must be in a particular form. Okay, so the equation itself must be in a particular form. And I'll give you the general form. So let's just write it must be in the form, okay, f at x is equal to, and I'm just going to write this out and I'll explain all the variables and exponents and letters used in a second. So I'll just write it out. Okay, so this looks like extremely complicated, but it's really not. Let's say, for example, I'll use an example so that I can kind of mirror what I have written there. Let's say I have an equation that looks like this. This is considered a polynomial equation, okay? And it follows this form right here. So you start off with a coefficient. Let's call it a subscript n, okay? And then you have an x, just like I have here. And our exponent it actually matches up with the subscript that is on this value. So let's say this is, one of four terms, right? One of four terms, or five terms, I suppose. Okay, so it matches up with here, and then you add another coefficient, but one less than that. So, and these coefficients, we're just calling them a subscript n. So let's say a5, and then the next one will be a4. So we subtract 1 from a5, and we get a4. Then the next one would be a3, and then a2, and then a1, and a0, and so on. And then our exponent goes 1 less than the exponent that was here. Okay, so the exponent goes 1 less than the exponent that was there. And then all the way to the point where I put a dot, 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 because you could have any number of degrees here. I mean, it could be 3x to the power of 10 and then go down from there. So I put a dot, dot, dot because it insinuates that it could go as high as you really want or as an equation can go. And then eventually at the bottom though, like at the lower end of the equation, you end up with an x squared, a coefficient with an x squared, a coefficient with an x, and then just a constant here. Okay, so these all match up. All right, so it's just the general form. You can see that my degrees are going down sequentially. So 4, 3, 2, and then a 1, and then have no degree on the 12 there. It's just a constant. Okay, but you can even skip, like your exponents don't have to go down in order like this. It could go from a 4 to a 2 to a 1. Like it may not have all these terms in the equation. Okay, but the idea is that's generally what it will look like. So it has to be in that form. Now, to say a little bit more about this is that the exponents have to be positive integers. Okay? They must be positive integers. What does that mean? It means that they must be positive values. Okay? Positive whole values. Or 0. They can also be 0, of course. But it has to be a 4 or a 3, a 2, a 1, a 5, and so on. It cannot be any negative integers. Okay? On top of that, it can also not be a rational number, meaning your exponents cannot be fractions. So exponents must not be rational. So I'm using the word rational instead of fractions. Okay, so that means it can't be a decimal, your exponents. You can't have a power of, 3x to the power of 2.4, okay, or 3x to the power of 1/2. You can't have that. That means it's not a polynomial function, okay? It has to be positive integers, and then they cannot be rational numbers. Okay, the coefficients can be any real number. So unlike the exponents, the coefficients, the numbers in front of the variables, these ones here, the coefficients can be any real number, meaning those coefficients can be decimals and fractions as well. Okay, they could be negative values. Like I said, decimals, fractions, it doesn't matter. The coefficients can be anything. Okay, now the term with the highest exponent, in theory and in common practice, it should be written first. Okay, so that's just common practice. So the term with the highest exponent should be written first. And what that does is that helps us determine the degree of an equation. Okay, and I'll explain what that is. So I'll just write that down. This highest exponent tells us the degree of the equation. Okay, so if it gives us the degree of the equation, what does that mean? This equation up here would be considered a 4th degree equation, okay, because the highest exponent is a 4. So that would be a 4th degree. If the highest exponent was a 3, then it would be a 3rd degree. If the highest exponent was a 2, it'd be a 2nd degree. If the highest exponent was a 1, it'd be a 1st degree polynomial, or 1st degree, 1st degree polynomial. Okay. This idea of knowing the degree, so understanding the degree actually helps us identify what the graph could look like. So understanding the degree of an equation helps us determine or identify what the graph could look like. So it's not saying that we know it accurately, but what the graph could generally look like. Okay? And then on top of that, the leading sign that's in front of our polynomial function. So let's say in this case, our leading sign, okay, is the sign that's in front of the very first coefficient with the very first term with the highest degree. Okay, the very first term with the highest degree, the leading sign. So in this case, it's a positive. Okay, so you look at the first term that has the highest degree, whatever that sign is, okay, that actually determines the direction of the polynomial function, whether it opens up or down, or if it goes from left to right, or if it goes up left to right, or down left to right. Okay, so that's another important factor, is the leading sign tells us some information. Okay, so the degree of a polynomial function gives us information on what the graph could look like, and then it gives to know the leading sign gives us even more, because then we know if it's opening, like I said, a quadratic is opening up or down, or a linear equation is going from left to right going upwards, or left to right going downwards. So that leading sign is important to us as well, and that should be noted. Okay. So, I mean, I already touched upon from my website why learn about polynomial functions. There's just so many applications. Okay, so let's jot a couple of them down here so it's in our notes. So profits in the business world. Okay, so we'll only jot down a few, but there are a lot. Profits in the business world, okay, generally follow some sort of polynomial function. It could be linear, it could be quadratic, it could even be cubic, but they often follow a polynomial function. And so why is that important? Well, it helps companies make predictions, right? So if you are able to model what your profits were like on a certain product or whatnot, if you were able to model it with a polynomial equation, meaning it's following a pattern of a polynomial equation, that helps you make predictions in the future. Okay, so if something is following kind of an up and down pattern, maybe it's following a quadratic pattern, for example. Okay, and so you can predict, just when that turning point is potentially. I mean, it might not be accurate, but you can predict when that turning point of going from up to down might be, if it's a quadratic that's opening downwards. Okay, so profits in the business world. Actually, reaction times to certain prescription drugs. Okay, that is another item that can be modeled using some sort of polynomial function, potentially. Okay, population growth. Okay, water flow. Okay, bridge design, like I had mentioned earlier. We're just writing down a few of them. Okay, and actually another one, planetary movement as well. Okay, so some movements of planets can be modeled using a polynomial function of some sort. It usually can be described using a cubic formula. Okay, so that's another example. The list goes on and on. Electrical resistance in semiconductors can be found using a cubic formula. Volume of a rectangular prism, of course, uses a cubic formula as well. Okay. So knowing everything that we have just discussed, here is a list of polynomial expressions versus non-polynomial expressions. All right. So here we have a polynomial expression following the exact pattern that I had said earlier. Notice that the degrees are going in order from highest to lowest. The highest degree is first. Okay. The exponents are positive integers. Okay. And there's no rational numbers in our exponents. Same can be said about this. Okay, even though that it skips, notice how it skips x to the 6, x to the 4, x squared, and x. That doesn't matter. Okay, so it doesn't have to have every degree. So let's say your highest degree is an 8. your function, your equation doesn't have to have below the 8 a 7, 6, 5, 4, 3, 2, 1. Okay. It's still a 7th degree function. It just will look different than an equation. The graph will look different than an equation that has all the terms, right? From 7, 6, 5, 4, 3, 2, 1. This equation will just look different. It'll follow the same behaviors, the same basic properties, but obviously be stretched and compressed and moved around differently. Again, another polynomial function. Remember, I said that the coefficients can be fractions. They can be any real number. Okay, decimals, fractions, doesn't matter. Same thing here. Square root of 4 is 2. Square root of 5, you get a decimal. You can have decimals as your coefficients as long as your exponents are positive integers and are not rational. Even something like -7, right? The equation of y equals -7, what does that look like? Well, it's a straight horizontal line, okay, through the y-axis at -7. So that is also a polynomial function. In factored form, so this is in factored form here, this would also be considered it. So it's no longer, this is not in standard form, it's in factored form. That can also be considered a polynomial function. Okay, and there's a linear equation there, a linear expression, also polynomial. In terms of non-polynomial, here we go. Why is the square root of x plus 7 not polynomial? Well, from the last unit, we know that the square root of x is equal to x to the power of a half. Okay, and again, what I had mentioned earlier is that you cannot have a rational number as your exponent. Okay, you also, what I actually didn't mention above, is that there can be no variables in the denominator, and that's something that we should add here as well. Okay, so no variables in the denominator, if there is a denominator, of course. Okay, you can have a number in the denominator and it still be a function, but you can't have any variables. So therefore, this is not a function. Okay, this one, not a function because it has an exponent with a negative integer, not a polynomial function. You can also, you are not able to have an x as your exponent. So a variable is your exponent. That's actually another one that we should add to this list. Okay, no variables, even though it's implied that I said that your exponents have to be positive integers, you cannot have any variables in your exponent. Okay, so we should add that to the list. So no. Okay, nowhere in my list does it say that you can have sine, cos, or tan. That is not a polynomial function. Okay, here we have a decimal 2.5 as our exponent. We cannot have anything but positive integers as our exponents. Okay, and here we have multiple variables in the same term. Okay, multiple variables in the same term also make it not a polynomial function. Okay, all right, let's move on. Be prepared to be able to identify between the two of them, okay, because they're great little short answer questions. Multiple choice or true and false questions. So be prepared for that. Okay, properties of common polynomial functions. All right, so let's look at some properties. So we're gonna have to understand what some of these definitions are. Okay, they're pretty, some of them we already know, some of them are pretty straightforward anyways. So let's start with the sketches. And actually I'll go through all of these one by one, so one column at a time. So let's start with a linear sketch. All right, so just really roughly a linear sketch. The degree. Okay, so the degree of a linear sketch. So let's give an example of y equals, let's say, 2x plus 1. Let's just use an equation as an example there. Okay, the degree, Okay, so the degree would be 1, right? The highest degree, the highest exponent is a 1. The leading coefficient, so what sign is in front of the term with the highest degree? It's positive. Okay, but it could be negative. It could be a line that is going down from left to right. So it could be negative. Is this odd or even degree? Well, if the degree is 1, that is an odd number. So this would be considered, any linear function is considered an odd degree. The domain and range. We know that the domain for this, it could be any x value, okay, that possibly exists. So x can be an element of any real number. And same with the y's. This line is going to go up and down forever in both directions. So y can be any real number as well with no restrictions. Now here's something new, the end behavior. Okay, here's how we're going to write out the end behavior. So what the end behavior is saying is what happens, okay, so what happens as this line basically approaches infinity to the right and infinity to the left. What is happening to my y's as a result? Okay, so what we'll do is we'll write it like this, and I'll explain. So as x approaches infinity, okay, y also approaches, and I should say positive infinity, y also approaches positive infinity. And as x approaches negative infinity, y also approaches negative infinity. Okay, kind of running out of space there, but let me explain. So here is positive infinity in this direction. And by the way, this symbol here, kind of like a sideways 8, is my infinity symbol. Okay, so you can do it any way you want there. But here's positive infinity on the x-axis. Here's negative infinity on the on the negative x-axis. And then on my y's, of course, my positive infinity goes here, my negative infinity is here. So the end behavior describes what the graph is doing at its limits. Okay, so towards the right, as x approaches positive infinity, this line is going up, correct? That means that y is also approaching positive infinity. And in the other direction, as x approaches negative infinity, this line is going downwards and y is also approaching negative infinity. So the end behavior describes what the line or the curve is doing at its limits. Okay, so as x approaches infinity, what's happening to y? As x approaches negative infinity, what's happening to y as well? Okay, so fairly straightforward there. The only new item for us, I think, would be the end behaviors, but it's not a difficult concept. Next, let's do a quadratic. Okay, not very neat. Let's try to do one a little bit nicer. Okay, so let's say this equation is y equals, I don't know, 2x squared. Okay, quadratic. My degree of my highest, so my highest degree here, of course, there's only one term and it's a 2. Okay, my leading coefficient is positive, but we know it could be negative. Is it odd or even degree? So if it's a degree of 2, then it's even. Okay, 2 is an even number. Your range, I know that it can be any x value, right? This is going to continue, this curve is going to continue in the left and right direction forever. So it can be any x value, but there is a restriction for the y. For this particular example, let's say that its vertex is right here at 0. Okay, just as an example, let's say that vertex is there at 0. So I would say here that y must be greater than 0. Okay, but as a general statement, y needs to be either greater than or less than. Okay, so less than or greater, okay, than the maximum or minimum value. Okay, so max / min. So you can call that any letter, right? So like for example, our minimum value here is 0, so y needs to be greater than 0. But your minimum value could be anything. You may even have a maximum value if your parabola opens downwards, right? So you could have a maximum value, in which case then your y values need to be less than that maximum value. Okay? End behaviors. As x approaches infinity, y approaches what? In this particular example, y also approaches infinity. And as x approaches negative infinity, y approaches, what happens when x is approaching negative infinity going this way? If this is positive infinity, this is negative. What is y doing? Y is still going up. So even though x is approaching negative infinity, y is approaching positive infinity. Oops. Okay. Next, a cubic function. So let's give an example of a cubic function. Let's say y equals, 3x cubed. Okay, that's a cubic function. The graph will look something like this. Okay, so it's got like kind of this, this bend in the curve here. Okay, and there's different variations of it. It doesn't have to look like that, of course. The bend could be more pronounced, like something like that. That can also be a cubic function. Okay, but I mean, we'll look at cubic functions in much more detail later on in this unit. So this is certainly a degree of 3. It's a 3. The coefficient is positive 3, so the leading sign is positive. It's an odd number. A degree of 3 is odd. What is my domain and range? It's actually identical to a linear equation. And you're going to see a pattern that all odd degree polynomial functions, so 1, 3, 5, 7, 9, they're all going to have domains and ranges where x is an element of real numbers and y is an element of real numbers. Okay, because they're going to have opposing end behaviors and they're going to go on forever in both directions. So XER, YER. And this would be true for all odd degree polynomial functions. Okay. Okay, end behaviors. Also identical to its linear counterpart, another odd degree polynomial function. Okay. As x approaches positive infinity, y also approaches positive infinity. And as x approaches negative infinity, y approaches negative infinity. Now, of course, remember that if it's possible that instead of the curve going this way, okay, that the curve could go this way. Okay, in which case you'd have the opposite. That is, x approaches negative infinity, y approaches positive infinity. Okay, so you just got to look at your graph to make that determination. Okay, but it will always be the same as its linear counterpart. So if it's a straight line going down this way, the end behaviors would be exact same as a cubic function that was going down in the same direction. Okay, they follow the same pattern because they're all odd degree. The same exact thing can be said for quartic and quadratic. So, okay, so even degree polynomial functions. Okay, so a quartic function can look something like this. So let's use an example of y equals let's do a negative 5x cubed, sorry, x to the 4. Okay, so something along those lines. It will look something like this potentially. Now it's not gonna, I know it's not gonna look exactly like this. Okay, and actually let's do a better job. So it can almost have like this W pattern, and it doesn't have to have that W pattern. This particular equation actually would be flat right there on the x-axis. But I just want to show you that a quartic function, I mean, it could go like this, it's almost like a wider version of a parabola, but it can also do like a W shape. So it can go like that, or an M shape, okay, whether it's opening up or down. Okay, so it is a degree of 4. In our case, our leading coefficient is negative. It's an even degree. Number 4 is an even number. The domain and range will mimic that of its quadratic counterpart. So it will always be XER, and the range will always be YER, such that y must be greater than or less than the min and max value. Okay, so it could either be, in this case, it would have to be, in my graph, it would be less than 0. Okay, y must be less than 0. You just look at where, if you have a min or a max value, and your y values need to be less than that in this case. Or if the graph is opening upwards, your y values need to be larger than the minimum value. Okay, end behaviors will mimic a quadratic. Okay, in this case though, in the case that I drew, as x approaches positive infinity, y is approaching negative infinity for this particular example. Okay, so as x approaches positive infinity, y approaches negative infinity, and as x approaches negative infinity, y also approaches negative infinity. Okay, so they match up. So there's just some properties of linear, quadratic, cubic, and quartic functions. The next question is, what do you expect the graphs of a degree 5 and 6 look like? Okay, so a 5th degree, let's compare it to a first. So if a first degree looks like this, okay, a 3rd degree potentially looks like this. What do you think a 5th degree might look like? If you guessed another turning point, you were right. So if cubic has 2 turning points, a 5th degree equation will actually have 4 turning points. So it goes from no turning points to 2 turning points here, to now having 4 turning points. And if you've recognized the pattern, the number of turning points is always 1 less than the degree. So if this is a 3rd degree, it has 2 turning points. If it's a 5th degree, it has 4 turning points. So let's try to draw that. 1, 2, 3, 4. Okay, so a 5th degree equation can look like that. What about a 6th degree? Well, if a 2nd degree equation can look like this, and a 4th degree equation can look like this, a 6th degree could look like, well, let's see how many turning points. Remember, there's always 1 less turning point than the degree. So look at the 4th degree. I have 1, 2, 3 turning points, right? 1 less. So that means a 6th degree will have 5 turning points. Okay? So let's try to draw that. 1, 2, 3, 4, 5. Okay, that's what a 6th degree polynomial function could look like. There's tons of variations of it. Okay, tons of variations. All right. Last thing here before we just kind of summarize is we're going to be determining the degree of a polynomial function just from a table of values. Okay, so far we've looked at how to determine one from a graph. Okay, so we've looked at the graphs of some different polynomial functions. We've looked at equations as well. So all the way at the top here, we looked at what constitutes a polynomial function just by looking at the equation. But what about a table of values? Well, if we recall, okay, let's start with a linear table that I'll show you. Then we'll do a quadratic table, and then I'll do a cubic. So I'll do 3 different examples here so that you can see that it does in fact always work. Okay, so let's start with a linear. So I'll do a table of values, and I'll say that my equation is, let's keep it simple, y equals 2x. Okay, so I'm going to make up my x values. I'll pick some easy ones, -1, 0, 1, 2. And I'll plug those values into my table so that I substitute -1 in for x. So what do I get for my y? -2. Okay, then 0, then 2, then 4. So finite differences is finding the differences of your y values. Okay, so these are now going to be considered my first differences. Okay, so my first differences. And then if I have to find more differences, then I would go on to my second differences, and so on and so on. So for linear equations or functions, what you do is you take 0, so the number, the second value, minus the first. So 0 minus -2 is +2. Then do 2 minus 0, +2. Then do 4 minus 2, +2. What you'll notice is that the first differences are what are called constant for a linear function. Okay? So it lines up, as you're going to see, your first differences are constant when your equation has a degree of 1. Next, we're going to see that in a quadratic example, actually, let's do this. Let's do a quadratic example, which is, remember, a quadratic has a degree of 2. It's a degree 2 equation. Let's do y equals 2x squared. Again, let's keep it simple. Let's come up with my values here, -1, 0, 1, 2 again. Substitute -1 for x. Okay, you get 2 times 2, which is 4, right? -1 squared is +1. Oh, sorry. +1 times 2 is 2. Then 0 squared is 0 times 2 is 0. Then 1 squared is 1 times 2 is 2 again. And then 2 squared is 4 times 2 is 8. Okay, now let's find our first differences. And what we're going to find is that they're not constant for a quadratic. Okay, so 0 minus 2, -2. 2 minus 0, 2. See, they're not constant. 8 minus 2, 6. But what you will find is that the second differences are constant. Okay, so if you now do 2 minus -2 is 4. 6 minus 2 is 4. So second differences here are constant. And remember, it's a degree 2 equation, so second differences are constant. Guess what's going to happen for a cubic table? The third differences will be constant. Okay? So I'm not going to actually do an example there. Just take my word for it that if we did a cubic function, the first and second differences will not be equal, but then if we took a third difference, they would end up being equal. And then for a quartic function to the degree of 4, the fourth differences will be constant, and the pattern continues on and on. Okay? Below here, you'll find a summary table, okay, which is really useful. It's probably going to be a little bit neater than the one that we did, but it's a great summary. Now, I actually gave examples in the summary in the table that I did, whereas here, they're kind of summarizing, in general, odd degree and even degree polynomials. They can each have positive or negative leading coefficients, okay? Then they go on and explain what their end behaviors are, okay? They look at what a possible sketch is for each one, okay? Here's what a positive, okay? So this is a positive cubic function. Notice it's going up to the right. A negative cubic function, just like a negative linear function, goes down to the right. Remember, we read left to right, right? We live in Canada, the Western world, we read left to right. So when you're interpreting and reading this graph, you're saying that it's going downwards, going left to right. Okay? A positive even degree polynomial will open upwards. And notice that it opens upwards and the end behaviors are the same. Okay, so the end behaviors are both going up. Unlike the cubic, one is going up, one is going down. When you talk about an even degree polynomial, like a quadratic or a quartic or a sixth degree, the end behaviors will be the same. So the arrows will be pointed in the same direction. Whereas an odd degree polynomial, the arrows will be pointed in the opposite direction, always, whether it's linear, cubic, fifth degree, and so on. Okay? Now they just go on to explain exactly what I've already explained. The domain and range for all odd degree polynomials will be this, very simple, XER, YER. For even degree, the domain will always be XER, but the range will depend on the maximum and minimum value. So they've identified that A, let A represent the max / min Y value. Okay? And so hopefully you have learned quite a bit of properties here regarding polynomial functions. Linear and quadratic should have all been reviewed. We learned a little bit more about cubic and quartic and what their graphs could look like and how they're related. So how a cubic function is related to a linear function and how a quartic function is related to a quadratic function. So these patterns exist depending on the degree of your equation. Odd degree equations will follow a certain set of patterns. Even degree equations or functions will follow a certain set of patterns as well. And the big new term that we used was something that we learned was something called end behavior. Okay, and it's looking at what is happening to the limits of our graph. So where the arrows are pointing, what is happening? As x approaches infinity, what is happening to y? As x approaches negative infinity, what is happening to my y's? Okay, that concludes this lesson of being able to identify polynomial functions.